Today we shall consider Myhill-Nerode theorem and minimization of finite state automata. This is Myhill-Nerode theorem. It states that the following three statements are equivalent. The first statement is the set L contained in sigma star is accepted by some FSA. The second statement is L is the union of some of the equivalence classes of a right invariant equivalence relation of finite index. Third, let equivalence relation RL be defined by X RLY if and only if for all Z in sigma star XZ is in L exactly when YZ is in L, then RL is of finite index. Okay. So, we will prove this theorem and then see that how this theorem can be used for minimizing an automata. We have seen in some examples where the same set will be accepted by two automata, but one will have lesser number of states than the other. So, how to minimize a DFSA? For that the idea in this theorem will be useful, and also we used pumping lemma to show that certain sets were not regular, okay. But then in some cases it was not easy to prove that something is not regular using pumping lemma. For example, we saw an example where the pumping lemma holds, but the set was not regular. So, another way of proving that something is not regular is by using Myhill-Nerode theorem. So, let us prove this result. There are three statements. So, we will prove it as 1 implies 2, 2 implies 3, 3 implies 1. So, that all of them are equivalent. First of all, let us recall what is an equivalence relation. What is an equivalence relation? The relation is defined over sigma star, the set of all strings over sigma here. When do you say that a relation is equivalent, is an equivalence relation? If it is reflexive, symmetric and transitive. So, if the three properties are satisfied, it is called an equivalence relation. What is reflexive means? X related to X, this is reflexive property. Symmetric property means X related to Y implies Y related to X, this is symmetric property. And what is the transitive property? X related to Y and Y related to Z implies X related to Z, this is transitive property. If these three properties are satisfied, the relation is called an equivalence relation. We have studied about this in the earlier course a lot. Now, the number of equivalence classes, an equivalence relation partitions the underlying set into classes, is not it? Equivalence relation corresponds to a partition and it partitions the underlying set into classes. The number of equivalence classes is known as the index of the equivalence relation. So, for example, if you consider the relation over the set of non-negative integers mod 3 relation, then you have three equivalence classes, those that leave the remainder 0, those that leave the remainder 1, those that leave the remainder 2, is not it? And you can also have infinite index. There are equivalence classes where you can have infinite number of equivalence classes, and so the index of the equivalence relation will be infinite. Okay. So, what we have to show that the set L contained in sigma star is accepted by some FSA implies that L is a union of some of the equivalence classes of a right invariant equivalence relation of finite index. That is the first portion of the proof we have to show. First portion is 1 implies 2. Again, this idea we have seen earlier. For example, a finite state automaton has a finite amount of memory, it only distinguishes between equivalence classes of input histories, that is what we said. The sort of adder, if you consider the adder, when you consider two binary numbers, if it produces a carry, you go to one state, if it does not produce a carry, you go to another state. And similarly, if you take a parity check, If it is even parity, you go to one state. If it is odd parity, you go to one state. Okay. So, it just distinguishes between two equivalence classes. So, those strings which produce even parity belong to one class, those strings which produce odd parity, they belong to another class. The number of equivalence classes is 2 there, is not it? The same idea we are going to use here. So, let L be accepted by a deterministic FSA, M is equal to K sigma delta Q naught F. Okay. And you define an equivalence relation Rm on sigma star. How do you define? If two strings x and y are related by Rm, okay, if delta of Q naught x equal to delta of Q naught y. Two strings x and y are related by the relation Rm, M standing for the machine, if delta of Q naught x is equal to delta of Q naught y. Why do you say that this is an equivalence relation? How can you say it is an equivalence relation? It has to satisfy the three properties: reflexive, symmetric and transitive. Okay. But this itself is defined using equality relation, is not it? So, equality relation has all the three properties: reflexive, symmetric and transitive. But anyway, you can check, is x related to x, delta of Q naught x is equal to delta of Q naught x, is not it? So, reflexive property is satisfied. If delta of Q naught x is equal to delta of Q naught y, delta of Q naught y will be equal to delta of Q naught x. So, symmetric property is satisfied. If you have an z, delta of Q naught z, if this is equal to this, if delta of Q naught x is equal to this and this is equal to this will be equal to this. So, if x is related to y and y is related to z, x will be related to z. So, transitive property is also satisfied, right. So, this is an equivalence relation. What is the index of this equivalence relation? The set of, there are n states in the automaton, say Q naught, U1, Qn minus 1. The set of strings which take you from Q naught to Q naught belong to one equivalence class. Set of strings which take you from Q naught to Q1 belong to another class, and so on. So, how many classes can you have? You will have at most n. Why at most n? The thing is, if some state is not reachable from Q naught, you can always remove that, but assuming such a state is there, that will not contribute to anything. So, the number of equivalence classes will be at most the number of states of the automaton. So, this Rm is an equivalence relation the index of Rm is at most the number of states of M. There are other things in the second statement. What you have to show is it is right invariant. What do you mean by right invariant? If x is related to y, for any z, x z should be related to y z. Take any string, if it is right invariant, the underlying operation is concatenation. So, this should imply that x z should be related to y z for any z, for any z. Then you say Rm is right invariant. This is very obvious. Suppose delta of q naught x is equal to delta of q naught y. What can you say about delta of q naught x z? That is equal to delta of q naught comma x comma z, right, and that is delta of q naught x is equal to q naught y, delta of q naught y comma z equal to delta of q naught y z. So, Rm is right invariant. In essence, it means that starting from q naught, after reading x or after reading y, you reach a state. Then from here, if you read z, you go to another state, right. So, starting from q naught, after reading x z, you go here, after reading y z, you go here. So, whether you read x z or y z starting from q naught, you go to this state. So, they belong to the same equivalence class, that is what it means. So, it is right invariant. One more point is that L is the union of sum of the equivalence classes of that relation. So, this equivalence relation Rm, if there are n states say, there will be one corresponding to q naught, that is I will call it as the equivalence classes, I will call as S naught, S1, Sn, supposing all states are reachable, Sn minus 1, n states are there. So, supposing all states are reachable from q naught, these are the equivalence classes, they are subsets of sigma star is partitioned into them. Now, this corresponds to q naught, this corresponds to q1, this corresponds to qn, that is this is a set of, if you have qi, it is Si. Si is a set of strings which take you from q naught to qi, right. Now, some of them will be final states. Among these states, some of them are final states. This is a final state, say this is a final state. Then there will be a class corresponding to that, there will be a class corresponding to that, right. So, L is the union of them, L is the union of such classes, because what is L really? L is a set of strings which take you from q naught to a final state. So, among these classes, some of them will correspond to final states, take the union of them, that will be L, right. So, what have we seen? If you assume that L is accepted by a DFSA with n states say, then you can define a relation Rm like this. It is an equivalence relation, it is right invariant, it is of finite index, and L will be the union of some of those equivalence classes induced by this equivalence relation. Is that clear? So, this is essentially this part, right. Now, we will go to this next implication, 2 implies 3. What is 2, what is 3? We will read again. 2 states that L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. Then 3 states that equivalence relation RL, let it be defined as XRLY if and only if for all z in sigma star xz is in L exactly when yz is in L, then the equivalence relation RL is of finite index. Now, we start with the E. Let E be an equivalence relation as defined in 2. That is, E is an equivalence relation on sigma star of finite index right invariant, and L is a union of sum of the equivalence classes. Then RL is defined as given in 3. You show that E is a refinement of RL. You show that E is a refinement of, what is a refinement? See, there is one equivalence relation which partitions the set like this, another equivalence relation something like this. These two belong to this, these two. R2 has, is an example, R2 has 3 equivalence classes, R1 has 5 equivalence classes. In R1, this equivalence class of R2 is divided into 2, this equivalence class of R2 is divided into 2. Then you say R1 is a refinement of R2. This is what we have studied earlier. That is, one equivalence of one equivalence class of R1 is completely contained in one equivalence class of R2. It does not split into 2. One equivalence class of R1 is completely contained in one equivalence class of R2. Then you say that R1, here we say that R1 is a refinement of R2. Okay. Now, what we want to show that E is a refinement of RL. Now, you have X E Y, that is X and Y belong to the same equivalence class of E. Then what can you say about XZ? It is right invariant. So, XZ is related to YZ for any Z. XZ is related to YZ by E, because E is right invariant. Is that clear? This is for any Z, for any Z belonging to sigma star. Now, L is the union of sum of the equivalence classes of E. So, if this equivalence class if L contains this equivalence class, then XZ and YZ will both be in L, isn't it? L will contain one equivalence class completely, or it may not contain anything. It is not that portion of the equivalence class it will contain and leave the remaining, not like that. L includes one equivalence class completely, or it excludes it. So, if L includes this equivalence class, both XZ and YZ will be in L. If L does not include this equivalence class, XZ and YZ both will not be in L. Okay. So, for any Z, either XZ and YZ both will be in L, or XZ and YZ both will not be in L. Is it clear? That is the condition of RL. X RL Y, if and only if for all Z in sigma star, XZ is in L exactly when YZ is in L. So, that means if this holds, this will imply that X RL X and Y are also related by RL. Is that clear? What does that mean? If X related to Y by E, X is also related to Y by RL, that means one equivalence class of E is completely contained in one equivalence class of RL, right. Maybe two equivalence class of E together form an equivalence class of RL, it may be possible. So, essentially X related to Y by E means X is also related to Y by RL. That is, each equivalence class of E is completely contained in one equivalence class of RL. Okay. That means, what does that mean? E is a refinement of RL. And what is the index of E? We started with the assumption that L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. Okay. So, what do you say? E is of finite index, index of RL is less than or equal to index of E, is not it? Because every equivalence class of E is contained in one equivalence class of RL, index of RL will be less than or equal to index of E. Therefore, RL is of finite index. So, what we have proved is 2 implies 3. Next we have to prove 3 implies 1. Okay. Before going into that proof, we will illustrate these 2 proofs by an example. So, look at this example. This has 3 states. This is a deterministic FSA and it has got 3 states, right. And what sort of strings will be accepted by this machine? Any string having at least one A will be accepted. Any string having one A will be accepted. A sequence of B's will not be accepted. If it does not have any A, it will not be accepted, right. So, sigma star you can divide into 3 classes, J0, J1, J2, 3 equivalence classes. J0 corresponds to strings which take you from Q0 to Q0, J1 corresponds to strings which take you from Q0 to Q1, J2 corresponds to strings which take you from Q0 to Q2. So, for example, here you will have epsilon B, BB, BBB and so on. This will have A, BA, BAB, BA, 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 and so on. And what sort of strings will be in J2? Set of strings which take you from Q0 to Q2, that will be AA, ABA, BA, BAB and so on. If you look to it carefully, set of strings which do not contain an A at all will belong to this class, just strings of B's alone. Any string having an odd number of A's will be in J1, any string having even number of A's will be in J2, right. So, sigma star is partitioned into 3 classes: strings which do not contain any A at all, epsilon is also in that, then strings which have odd number of A's, strings which have even number of A's. J naught has just epsilon and B's, this has got odd number of A's, this has got even number of, okay. And what is L? Isn't it? So, you can see that starting with a DFSA, you find that it divides sigma star into equivalence classes. Its finite index 3, index is 3 here, right, and L is the union of sum of the equivalence classes. Of course, it is right invariant, this is also right invariant, because if 2 of them belong to the same class, if you follow it with the string having even number of A's, you will go to the same class. If you follow it with a string having odd number of A's, you will go to this class. Anyway, it is right invariant. If 2 strings belong to the same class, x and y, x is z and y is z also will belong to the same equivalence class, okay. So, it is right invariant, and L is the union of 2 of them, J1 union J2, okay. So, I will just write like this. Just take as a sample only one string. Now, how are they related by RL? RL, how do you define? RL is defined like this: X RLY if and only if for all Z in sigma star X Z is in L exactly when Y Z is in L. So, you find that if take for example one string from here, one string from here. See, RL has to be such that this is a refinement of, I mean the equivalence classes, either you can have 3, 2 or 1. In RL the number of equivalence classes will be, it will not be more than this, it will be, it can be 3 or it can be 2 or it can be 1, right. So, you have to find out whether 2 of the equivalence classes can be grouped for RL, okay. Now, if you take a string from here and if you take a string from here, say for example B and A, you follow it by B, follow it by B, BB is not in L but AB is in L, right. So, they are not related by RL. So, this and this cannot be the same equivalence class for RL. Now, take from J naught and J2, take B and AA, take Z as B, 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 this is not in L, this is in L, right. So, again J naught and J2 cannot be grouped together in RL, okay. Now, take 2 strings in J1 and J2, say W1 and W2, take any Z. After reading Z, you are after reading W1 you are in Q1. After reading Z, either you will be in Q1 or in Q2, you cannot go back to Q0, right. Whatever may be Z, after reading W1 you are in Q1, after reading again Z you will be in Q1 or Q2, whatever it is W1 Z will be accepted. Similarly, W2, starting from Q naught, after reading W2 you go here, then read Z, you will be either in Q1 or Q2, you are not going back to Q naught. So, that will also be accepted. So, W1 whatever may be Z, in this case W1 Z and W2 Z both will be accepted. Okay. So, you can group them together, J1 and J2 can be grouped together. RL has only two equivalence classes, J0 and J1 union J2. This is RM. So, index of RL is, what is the index of RL? 2. Okay. Now, you have to show 3 implies 1. This completes the proof. Okay. Now, how do you first of all show that RL, prove RL is right invariant. First prove RL is right invariant. How do you prove this? The definition of RL is XRLY if XZ is in XZ belongs to L is equivalent to saying YZ belongs to L. Now, instead of taking Z, I take WZ, that is XWZ, this can be anything, right. So, I say XWZ belongs to L is saying equivalent to saying YWZ belongs to L. Whatever may be WZ for all W for all Z, is not it? Instead of saying Z, I can take WZ, does not matter, is not it. So, X whatever may be W, whatever may be Z, XWZ belongs to L implies equivalent to saying YWZ belongs to L. That means this is for any Z. So, what do you conclude? XW related to YW. When can you say XW is related to YW? Whatever may be Z, XW is Z and YW is Z, either both of them should be in L or both of them should not be in L. So, from this you can conclude that XW is related to YW. You started with this and you have come to this. What does that mean? What does that mean? RL is right invariant, is not it? So, therefore, RL is right invariant. You define a FSA, define an FSA m dash is equal to k dash sigma delta dash q naught dash f dash as follows. For each equivalence class of RL, we have a state in K dash. corresponding to each equivalence class of RL you have a state in K dash. So, what is the number of states of K dash? Index of RL, this is equal to index of RL. Now, if X is a string, if X belongs to sigma star, denote the equivalence class of RL to which X belongs as X within the square bracket. So, we have defined K dash, sigma is the alphabet, Q naught dash, is the equivalence class to which epsilon belongs. Empty string belong to one of the equivalence classes, that equivalence class corresponds to a state and that is the initial state. Okay. And define like this, delta dash X comma A, this is an equivalence class, it is a state which represents the equivalence class to which X belongs, right. Then after reading a symbol A, to which state does it go? It goes to the state X A, defined like this, and this is a consistent definition because of right invariance. This definition is consistent because RL is right invariant. See, instead of saying say X comma A, delta of X comma A, you can X and Y, suppose X is related to Y, you could write like this also, nothing changes, you are allowed to write like this because X and Y here you can write X or Y, they belong to the same equivalence class, and by right invariance XRL YA. So, whether you write XA or YA does not matter, they belong to the same class and one state corresponds to one equivalence class. Okay. So, the consistency comes because of the right invariant property. So, we have defined K dash, sigma is the same, delta dash, Q naught dash. What is F dash? F dash corresponds to those states some of them will include, some equivalence classes will be in L. So, make those states as final states, that is all. Then you will that is assuming 3, assuming this portion you are defining an equivalence relation R such that X R L Y if and only if for all Z in sigma star X Z is in L exactly when Y Z in L. In this case you show, and RL is finite index, then you show that it can be accepted by a FSA. So, assuming this we have constructed a deterministic FSA in this manner. Now, let us go to this example and continue with this example. Now, you have seen that RL has 2 equivalence classes. So, if you want to construct a finite state automaton, it will have 2 states. one state will be J naught, another will be J1, and epsilon, you can see that epsilon belongs to J naught. J naught contains epsilon B, epsilon like that. So, this will be the initial state, and J1 this equivalence class, and they are corresponding to final states, right, and whichever is in J1 it will be accepted, whichever in J2 it will be accepted. So, this is the final state. How are the transitions defined? Starting from J naught, after reading a where will you go to? Starting from here, after reading a go to Q1, right. So, that is start with epsilon, after reading a you go to this equivalence class, right, delta of Q naught delta of J naught A will be J1, right. So, it will be A. Starting from here, after reading a B you will go to Q naught itself, that is if you are in this equivalence class, something is there X, then after reading a B it will be again in this equivalence class. So, it will be like this, and similarly you will see that you have these transitions. Okay. We can very easily see that they accept the same language. Any sequence of B's alone will not be accepted, epsilon will not be accepted, but if the string has one A, afterwards whatever you get is immaterial, it will be accepted. If you get one A, then whatever you get it will be immaterial. So, what you have done really is you have joined these together, you have merged the two states, okay, and you have got this. The same set is accepted by this, but this is a minimum state automaton. So, this is the minimum state automaton. So, we have proved the Myhill-Nerod theorem, and making use of Myhill-Nerod theorem we can minimize an automaton. Given a deterministic FSA, you can find the minimum state automata. Another use of Myhill-Nerod theorem is to show something is not regular. Let us consider minimum state automata in the next lecture. We will just show how to make use of this Myhill-Nerod theorem to show that certain sets are not regular. Use Myhill-Nerod theorem to show certain sets are not regular. Take L to be a power n, b power n, n greater than or equal to 1. We have used pumping lemma to show that this is not regular. Actually, you will find that in some cases it is easier to use Myhill-Nerod theorem. Some cases pumping lemma is easier to, depending upon the problem you have to see which one to use. Now, we want to show that this is not regular. So, how do you prove? Suppose L is regular. Suppose L is regular, then what do you conclude from the Michael-Nerod theorem? Then by Michael-Nerod theorem, L is the union of, okay, the statements we can make. L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. So, that equivalence relation divides sigma star into equivalence classes and they are finite. Now, consider the strings A squared, A cubed, A power 4, they are all belonging to n. They are all belonging to sigma star. Now, all of them cannot be in different equivalence classes. The number of equivalence classes is finite, is not it? The number of equivalence classes into which this is divided, is not it, is finite. So, all cannot be in different equivalence classes. That is, each one cannot be, I would rather put all, each one cannot be in a different equivalence class. Isn't it? You have A squared, A power 4, etc. All of them cannot be in different equivalence classes, some of them have to be in the same equivalence class, right. So, for example, A power m and A power n, for some m and n, m not equal to n, they are in the same equivalence class. You write it in this symbol. A power m and A power n are in the same equivalence class. Now, because of right invariance, what do you have? Because of right invariance, A power m B power m and A power n you multiply or you concatenate with B power m, these two will be in the same equivalence class. Now, L will contain one equivalence class completely or it will not contain that equivalence class. If L, see, A power m belongs to L, A power m, B power m belongs to L, right. But L should contain that whole equivalence class, is not it? L should contain the whole equivalence class. That is, A power n, B power m also belongs to n, where n is not equal to m. You come to this conclusion, you come to the conclusion that A power n, B power m belongs to L, where n is not equal to m. This is a contradiction, because the language is only A power n, B power n, equal number of A's followed by an equal number of B's, isn't it? So, you are arriving at a contradiction, therefore, L is not regular. So, in some cases Michael-Nerod theorem is easier to apply rather than pumping lemma. Pumping lemma, sometimes it becomes a little bit difficult to apply. Okay. So, these are two ways of proving that set is not regular, and Michael-Nerod theorem can be used to find the minimum state automata. This we shall consider in the next lecture.